KMT is short for kinetic molecular theory. So far we've considered what happens, but not why it happens. In science, what always comes before why. So let's look at the kinetic molecular theory. You can see that in picture A, where we're talking about a liquid, like liquid water, liquid nitrogen, it's probably liquid nitrogen if we look at the molecules carefully because there's only two of them, but you can see that the molecules are very closely packed together. And 1 mole of that, if it were to become a gas, would fill 22.4 liters. Notice how those molecules are more energetic and they move around and they're further spaced apart. The particles are so small compared with the distances between them that the volume of the individual particles can be assumed to be 0. So there's so much space in between, we assume that it's almost like gases aren't even there. The particles are in constant motion. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. So if you have a balloon, and you have particles in there, when this particle, for example, collides with the wall of the balloon, it exerts a force on the balloon, and then it bounces off and it goes in another direction, etc. And it keeps moving in a path and it continues to create pressure. The more gas that's in there, the more pressure. The higher the temperature, the more pressure. Or the smaller the volume, the more pressure. The third postulate is the particles are assumed to exert no force on each other. They are assumed to neither attract nor repel one another. So those points just kind of bounce around and move around. And the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. Remember, temperature is defined as average kinetic energy. So when you see the word temperature, you can substitute the word or the phrase average kinetic energy. And if you see the phrase average kinetic energy, you can replace it with the word temperature, and sometimes that helps answer particular questions. So here we have an example. Complete the following statement with different or the same and be prepared to justify your answer. The pressures of the gases of the two balloons are. Now, it's kind of interesting because they really don't give you too much information here, except for two lovely pictures of helium and hydrogen. It looks like they're about the same volume, and we would assume that they have the same pressure, and we would assume that they're at the same temperature, although, to be honest with you, they might not be. But since we don't know anything different, those two balloons look like they're in the same location. So therefore, what about the pressure? They're going to be the same. These are the I'm going ahead of the questions. Moving ahead. Moving back to move ahead. How about the temperature of the gas in the two balloons? Well, I think I already mentioned we're assuming that they are the same. So they occupy the same volume and have the same pressure. They are probably the same temperature. What about the number of moles of gas in the two balloons? Well, we already know at standard temperature and pressure, 1 mole of a gas will occupy 22.4 liters. So we can again assume that the densities are equal. What about the density of the gas in the two balloons? Now density is mass over volume. We know that helium and hydrogen have different molar masses. Helium has a mass of about 4 grams, and hydrogen has a mass of about 2 because each one is worth 1. So they may have the same volume and the same number of moles, but each atom of helium is heavier than each atom of hydrogen. Therefore, the densities of the two balloons are definitely different. Root mean square velocity is the formula U, RMS, which means root mean square, equals the square root of 3RT over m. R here is gas law constant again, but this time it's 8.3145 because the other units allow it to cancel. As you can see, T is temperature, and m is the molar mass of the gas in kilograms. Now I'm going to circle that because oftentimes we have molar mass in grams, but here, to make the units cancel, for joule, as you see above, you'll have to have kilograms. And the final units are meters per second. So this is a unit of velocity, as you might remember from physics. Effusion and diffusion. Two interesting concepts. This just has to do with how gas moves through space. Diffusion is the mixing of gases. Effusion describes the passage of a gas through a tiny orifice into an evacuated chamber. Almost like, I think of effusion as like a pinprick in a balloon. The gas coming out of the balloon would be going through a tiny opening. Now here specifically, it's into a container that's empty. And the rate of effusion measures the speed at which the gas is transferred into that particular chamber. Different factors, of course, affect that. Here is Graham's law of effusion. I know we've had this before. The rate of gas 1 as compared to rate of gas 2 is actually equal to the square root of their molar masses. Notice, however, gas 1's molar mass is on the bottom and gas 2's molar mass is on the top. M1 and M2 represent the molar mass of the gas. We must be correct for non-ideal gas behavior when pressure of the gas is high and temperature is low. So ideal gases, that's the vast majority of what we're dealing with, but sometimes we're talking about real gases, ones that might deviate from ideal behavior. So what are those conditions? These are the two. Pressure of the gas is extremely high, and if pressure is extremely high, you know those molecules are very, very, very close together, almost perhaps changing from the liquid back to the from the gas to the liquid state. And if the temperature is low for a gas, again, it starts to liquefy, and it gets to deviate from the behavior of a gas because it might be close to its point at which it's changing into another phase of matter, like a liquid. Under these conditions, the concentration of gas particles is high, and the attractive forces become important. We'll revisit attractive forces, things like hydrogen bonding, dipole-dipole force, or London dispersion forces. But these are the other factors that come into play when molecules get closer together. You can see if we plot PV over nRT, PV divided by nRT versus P for several gases, you can see that when we have extremely high pressures or extremely low temperatures, extremely high temperatures, pressures, yes, and extremely low PV over nRT, you can see we're deviating from this dotted line a great deal. And again, a plot of PV over nRT versus pressure for nitrogen gas at 3 temperatures specifically, you can see as the pressure gets high, you see we really are deviating a great deal from standard conditions that we talk about, or the ideal gas conditions. So ideal gas law works beautifully for most things that we're dealing with, but in extreme conditions of pressure and temperature, the PV equals nRT gas law really doesn't hold true for us. You notice atmospheric pressure, 1 atmosphere, you know, way down here somewhere, is what we tend to be dealing with. So you can see in the average kinds of pressures we would have. Most gases act like an ideal gas. Only when you have extremely high pressures do things change.